Good afternoon, good evening, and good morning. Greetings from Stanford University and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber Event. My name is Renate Fruchter, Founding Director of the PBL Lab and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. In preparation for this year's May 8th cyber event, we had to be creative as we are all geographically distributed over 8 time zones. For this purpose, each global student project team prepared a video story of their project evolution. These stories were reviewed and assessed by 30 industry mentors prior to the May 8th event. I have to say, we miss everyone back at Stanford for this event to celebrate the end of the AEC journey together. Nevertheless, we are really excited to see today at our May 8th final presentation Zoom live cyber event a great turnout of 89 participants that includes the global students and 57 industry and faculty mentors. Each team will present a TED-style project team pitch to give everyone an overview of their proposals, followed by a Q&A discussions of their concepts. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentation.
So good morning, good afternoon, and good evening, everybody. We are Team Atlantic 2020. The team consists of Maria, myself, MEP engineer from Copenhagen, Brandon, our structural engineer from Stanford, Ibrahim, the construction manager from Madison, Xuan, our second construction manager from Beijing, Isabella, our architect, and Lewis, the other structural engineer, both from Brisbane. Our goals stem from who we are as a team, what we want to achieve in the project, and what we believe that we can achieve for the community through architecture, engineering, and construction. These can be categorized into three overarching categories: sustainability, collaboration, and technology, and relate directly to the outcomes that we can achieve in the project. We believe in resilience, fostered through community inclusion, compliance with elite standards, adaptability, and smart design. And we aim for a design and construction outcome that is prefabricated and disassemblable. Our project is located at the fringe of the campus of the University of Wisconsin in Madison, located in the Midwest of the United States. While presenting opportunities for its viewers, our site is constrained by its lakefront location, single-site entry, and limited access. As per hazards, we have taken the site's climate and climate change as the main driver. Our site has extreme cold and snowy days, but considering the future, this will be turning into warmer and more rainy days. Our aim is to design a tight building envelope in a short time due to the weather conditions and be able to manage and mitigate the water inside.
Our team's process and conceptual driver is weaving, which implies the process of combining and integrating. We drew on the local historical practice of weaving, which extends from the basket weaving practice of traditional owners to textile production as a part of the arts and crafts movement. Weaving unifies the threads of sustainability, technology, prefabrication, and discipline knowledge in a building for the future. The building product synthesizes the challenges of the previous iterations into an offering that interacts with its spectacular geography and evokes weaving through pattern, texture, and the interplay of light and shadow. It creates a place for learning, teaching, and making for a new generation of engineering professionals. At the ground and mezzanine levels, learning spaces are centered around the connective stair, which connects levels physically and visually. At the first floor, faculty offices are gathered around a central open workspace, which allows staff and their students to meet and collaborate informally. The planning fosters connections between the building users through functional, delightful spaces, and the weaving concept extends into the planning, with work pods weaving learning spaces into the public areas. Within the building, pattern created through opacity and transparency at the facade creates a dynamic, warm learning space throughout.
All disciplines have worked together to integrate a design. A primary challenge was to create a design responsive to daylight and energy efficiency. Through collaboration with Isabella, our architect, the areas have been grouped together with similar positioning and thermal conditions. The ventilation is decoupled from the heating and the cooling systems, and this allows downsizing the equipment, reducing costs, and energy and space needs. The indoor air quality is achieved through the fresh air, while thermal comfort is provided by electronic doors and radiators placed in specific spots according to the thermal demand.
For our structural system, we chose to use timber materials. In our grid system, we use one column size and only two different beam sizes. Our core walls, represented by green rectangles, and are constructed of CLT panels. Our grid system is actually concentric to the facade providing uniform support to the CLT floor slabs along the building's perimeter. The beams in our grid were designed to not frame into the facade due to structural and constructability difficulties. Furthermore, disassembly of the facade would compromise the integrity of the building if beams were the framing into it. It can also be seen here how the MEP aligns with the grid weaving within the structure. By having an exposed timber system, the mechanical systems were placed beneath the structure to allow for easy integration.
The auditorium provides a flexible learning and presentation space with retractable seating and mechanized track shading that allows the space to be used in a multitude of ways. The second building entrance at the south carves an activated concourse through the building interior and provides views through to the lake at the north upon entering the building from the campus side. The folded exterior expression is continued inside to create an inviting and dramatic procession into the building. The use of timber within the interior design fosters a connection between the material experience of the building and its construction elements, framed against glimpses of Lake Mendota. The interior experience offers a synthesis of the geometry of the building form, discipline-specific requirements for each space, and the learnings from all previous iterations into a building for teaching and collaboration.
Technology has allowed us to deliver an integrated building solution for our owners. By leveraging it appropriately, it has allowed us to create a highly interoperable, streamlined, and value-driven workflow. Our intelligent workflow contains the optimal combination of processes which maximize the value. These criteria were used to assess where, how, and which processes should comprise our integrated, intelligent, interoperable workflow. The selected combination of processes allowed us to synthesize geometric complexity, ease discipline dependencies while iterating quickly, selectively optimize our design, and create value for our owners. This end-to-end integrated workflow, facilitated through universal translation of information via SPECKLE and a single source of truth, has enabled the live linking of our design processes across the globe. Our technological solution not only unifies discipline drivers, but implements practicalities of industrialized construction and design for disassembly. Within the design and modeling stage of the workflow, the facade was parameterized to ensure technical resolution of our design for disassembly. Then, with the manufacturing and construction stage, the system assesses the risk and reward for the prefabrication solution. Grasshopper and SPECKLE were selected as the driving platforms of analytical, design, and discipline interoperability. As a team, we use SPECKLE to connect the processes of each discipline across the globe. This video demonstrates the efficiency of one process within our workflow. The facade geometry was pushed by myself to SPECKLE and retrieved by Maria in the daylight analysis script. The analysis was run and the results pushed back to SPECKLE and retrieved by myself in our central Grasshopper script for data aggregation. This data would then be pushed to our interactive web browser. The Grasshopper script forms a central location for all disciplines, with cross-disciplinary information able to be pushed and pulled as required. The system is set up such that it allowed users of all experience levels, including Maria with no prior Grasshopper experience, to receive its full functionality. Immediate translation of data between disciplines and the automation of processes such as the daylight analysis allowed for efficient and fast iterations and ultimately the elimination of aborted or repeated work.
It's through the integration of technology that we were able to test, learn, and iterate for the key challenge of the project, the facade design. Design for assembly, disassembly, and reassembly required an intensive process of iteration to ensure its feasibility across all project and discipline criteria, such as perimeter structure, daylight, and expression.
In synthesizing these goals and discipline drivers, we created a prefabricated engineered timber facade executed with 3 different module types. This solution reduced on-site activity, construction time, carbon footprint, and easy assembly and disassembly. Our facade is both architectural and structural. The CLT floor panels will sit within the facade, and the narrower vertical modules are stiffer load-carrying elements, and the wider modules framing above and below the glazing are the non-structural timber modules. To ensure that our facade was structural and architectural and designed for disassembly, we had to develop our solution to a high level of technical resolution. This is made possible through our end-to-end integrated workflow. Our connection details were designed to allow for ease of initial construction and designed for disassembly. These timber connections are hidden from the public eye, but are essential for construction speed and efficiency. We also devised a system where the core timber panel is on the inside of the built-up module, and then moisture protection, insulation, and flashing is enclosed within the timber cladding. The insulation and flashing overlaps from one module to the next to ensure continuous protection from the elements within the timber cladding. We use parametric design to produce the module assemblies and minimize their variability. while balancing this against the registration of weaving through pattern and alternation. We've conceptualized a kit of parts that emulates IKEA's assembly instructions. Facade panels, CLT floor panels, beams, and connections can all be reassembled to adapt to the changing requirements of its users and its context. The facade is constructed floor by floor with 5 different module assemblies. Each floor is 5 modules high with timber modules on the top and bottom for erection and glazing modules woven in between them. The tolerances are critical but can be achieved through industrialized construction. The vision for Team Atlantic's design was to allow the building owners to prepare for and adapt to future adverse events. Implementing a disassemblable building has required a high level of non-destructive detailing in connection design. Connections have been selected for flexibility in different configurations and reassembly, and to ensure that no damage to panels for future reuse. Glazing and non-structural timber panels can be reassembled in any arrangement. The flexibility of the solution eliminates the need to predict future use. Rather, it is designed for uncertainty. Here we can see one of the many potentials for what the building could become at the end of life. While the panel sizes are designed for uniformity and breadth of building application, the Atlantic building would be perfectly suited to the creation of social housing, especially relevant considering the broad disparity between high and low income earners in the United States. This potential use contributes to the resilience not only of the single building, but of the community as a whole. Ultimately, our answer to resilience has been multifaceted. It includes water-sensitive design, reuse, and reduction, as well as adaptable spaces such as the auditorium, and a building solution intricately and expressly designed for assembly, disassembly, and reassembly.
The sustainable target value has affected the decision-making process of the team. A summary of key decisions affecting the carbon cost of the building is shown here. By choosing a mass timber building, we have further improved the sustainability of our project. The weaving harnesses the sun with 224 PV panels placed on the roof, which account for almost 50% of electricity demand, and finding energy efficient solutions has allowed us to reduce our carbon footprint and reduce consumption of resources.
Target value design was used to value-driven improvements involving all team disciplines. The cost tracking timeline here shows 3 major design changes, which reflect team collaboration and decision-making. Integration of costs within the iterative process resulted in a project exceeding owner-driven requirements and coming in 22% under total allocated budget. The following framework was developed to provide real-time integration, starting from design and engineering, then manufacturing, construction, and visualization. This enhanced the overall agility of the team to iterate, measure, and implement design changes and quantify their impacts. Using Rhino, Revit, Grasshopper, the Atlantic team used parametric design effectively to investigate refabrication opportunities of the facade at the module level. Fragmentation in the supply chain was one of the risks identified earlier. Thanks to Manufacton, Atlantic team was able to track status of prefab orders utilizing supply chain viewers. We quantified total productivity gains when shifting work offsite, enhancing productivity by 30%. Manufacton allowed for real-time assessment of design impacts on industrialization through automated generation of bill of materials for prefab orders. This helped in quickly identifying sub-assemblies, quantities, and automating the cost estimation process. Finally, we managed to track productivity gains and mitigate risk for each step in the production line. AnyLogic was used to simulate and optimize processes through comparison of transportation and installation scenarios. The first scenario is fully prefabricating the panels, and the second is to prefix connections on site. Using AnyLogic simulation, 2 KPIs were investigated. First, the total time needed for shipping and an installation of panels, and the second, the pre-assembly area required. Risks associated with both scenarios, such as tolerance accuracies and coordination delays, were also modeled. The fully prefabricated alternative yielded better results in all areas. With the introduction of smart scheduling and planning technologies, site logistics simulations were able to occur iteratively alongside the schedule. Consequent risks and rewards were quantified through metrics derived through the iterative process. Logistical challenges on site were able to be forecasted and resolved iteratively with Fuser and Alice. Revised schedules and sequencing were output from Alice to resolve on-site issues, which were detected by Fuser. These technologies allowed the detection and visualization of congestion during the peak workflow day activities as seen in the video. Understanding the impacts of peak workflow activities allowed the team to foresee and mitigate construction risks. The last step was to investigate how constructability, safety, and logistical issues can be mitigated early in the design process. After changes are discussed on the team level, they are augmented with the integrated model. Integration of clash detection using VR software within the design phase eliminated rework and increased interdisciplinary reworks. Following integrated project delivery principles, Atlantic team developed an Excel tool to assess risk and rewards associated with the design decisions and industrialized construction solutions. The tool was utilized to assess alternative design decisions from risk and reward perspective. This process supported clear and quantified feedback within the team, therefore promoting transparency and trust among team members, as well as extra disciplinary ownership and involvement.
Our end-to-end integrated workflow quantifies risks and rewards, allowing our team to make justified decisions on industrialized construction and design for disassembly. As well as this, it has allowed our interdisciplinary processes to be live linked and dissolve our team's discipline and location-based boundaries. Finally, key design information and decision-making metrics were able to be extracted and centralized, allowing the Atlantic team to make smarter decisions and iterations across the project. The interactive public web browser allows anyone from team member to mentor to owner to participate in and experience our progress in solving our key challenge of the facade design. The centralized platform is the capstone product that connects the integrated design team to the end users, allowing the owners to engage with the building through design, construction, and future operation.
This project has been a massive and challenging endeavor. So much international and industry collaboration has been essential to the accumulation of knowledge and experience on this project. We appreciate every phone call and every email we've exchanged with all of you volunteer mentors. Most importantly, we recognize and appreciate the unyielding time and effort Dr. Renate Fruchter has put into this coursework and team experience for us all. We invite you all to join us and experience the application for yourself and get a better insight into how our facade became what it is today. Thank you.